Hi, in this video we'll be talking about an application idea. So without any further delay, let's just get into the problem. So we are given an array ARR of size n and initially all zeros. Okay, so you need to process q queries of the form plus ADLR, and so this is an update query, and ADLR, four numbers are given to us, and you need to add the AP A plus D, A plus 2D, so on up to the last value in the range L to R in the array ARR. Okay, so the L index gets as addition of A, L plus 1 index gets an addition of A plus D, L plus 2 index gets an addition of A plus 2D, and so on up to last range value A of R actually gets an addition of A plus R minus L times D. So this is how you get the AP terms, right? So there are q such queries that are happening, and after each of the query you need to find the final value of the whole array. Okay, so let's have a look at a example. So we need to add a AP of 2 and common difference 1, so this would be 2 3 4, right? 2 3 4, so on, right? This AP, you need to add this AP into the range 3 to 4. So if we quickly look at this cell number 0 1 2 3 4 5, so you need to add contribution of this AP into 3 and 4, right? Just this small subarray. So the first two terms get added and you get a contribution of 2 3 in this two cells. Next we have this plus 1 2 1 5, so it gets added to the range 1 to 5 and it has starting value 1 and the common difference as 2. So you have 1 3 5 7 9, so on, right? These are the values, and you need to add this in the range 1 to 5. So you need the first 5 values, and the values that are being added is 1 3 5 7 9, and the final values in the array would now be like after both the queries have been run. So these things would get added in the cells correspondingly, and the values would be 0 1 3 7 10 9, right? So this would be the final array that you need to print. So let's have a look at the contribution carefully to solve this problem. So you need to add plus ADLR, right? Now this is a very generic term, right? We need to have a look at what this actually is adding at every index. So at every index you are adding this term over here. How? So the first term is A, then A plus D, A plus 2D. So if you write a general term for that, the array ARR of I gets the addition of this value in the range L to R, right? This is only true in the range L to R. Okay, so this is the contribution that you're getting at the ith index. So if you put in I equal to L, so you get A. If you get L plus 1, that is A plus D. So corresponding to every index you're getting the correct contribution, right? Even at the last value you put in R, you get this expression, and that is actually given in the problem, right? That is actually given in the problem, this value over here. So this is what we're getting over here. Okay, so now this is the contribution as a general term where I is in L to R. So we can also write it by opening up this bracket and just shifting things from L from over here to the second term. You get A minus LD plus I times D, right? Now if you look at this carefully, there is this two part in this expression. There is a minus LD part and there is this I times D part, right? Now this A minus LD part is actually constant for every query. So once you are given the query, the value of L, D, AR are constant, right? So in the range L to R, every ARR of I gets the addition of this in a constant way, right? So this is like some constant C that is being added to the range. Okay, so if you had to add a constant to a range, we know how to do that. We can just use the partial sum technique, that we can add this at Lth index and subtract this from R plus 1th index and then just build a prefix sum. That would work for this. But there is this weird term over here, that is I into D, where there is this I is getting multiplied, and that is dependent on position, right? So we cannot really process this directly using prefix sums or the direct partial sum technique that we discussed about. So how can we make it independent of I? How, like, as long as there is a I in the term, we cannot really process that directly. So how do we make it independent of the position? So what do we say to ARR, that now ARR would be actually contribution of two arrays. So we create two arrays A and B, and once the values of both of them are being created, the final ARR array that we need would be A of I plus B of I times I. Okay, so that is the final ARR value that we would be getting, and we would be creating these two A and B arrays separately, and then we know the final array would be this. So this is assumption right now. This A and B has no real meaning. Okay, this is something that we are creating for our own help, and we would be using this relation written over here, A of I plus B of I times I, as the combining rule, that once we have these two arrays, we will be combining it in this fashion, that A of I plus B of I times I will be the value of ARR of I finally. Okay, so we try to build the A and B arrays and then get the final array ARR. Okay, so now when we were doing addition, we had this general term over here, right? A minus LD. Now this is a constant term, right? And now we want to have this constant term getting contributed to ARR in a constant way, like every index in L to R gets a contribution of A minus LT. So what we can do is that we can add this to the range L to R in this A of I array, because whatever the values in this range are, they will finally get contributed linearly, like whatever, if there is C over here, that gets added to ARR. So if this value over here is getting added to this position, this positions in the A array, that would be getting transferred into the ARR, right? Also there is this I into D part, right? So for that, what we can do is that we can pass this D part into the B array, and we know that when we will finally combine, we would be multiplying the things with I and then contributing it to ARR. So if we add just D in the range corresponding to L to R in B, we would finally get D times I in the ARR. So that really helps us with the problem a bit, because now this is like a constant that is being added to A, and this D is a constant that is being added to B. Okay, so let's have a look at an example. So let's say you need to add the AP with the first term X and a common difference Y in the range 1 to 4. Okay, this is what we are doing. So if we like write a general expression and open it up using this expression over here, you just get this value. Okay, so this is the constant, that this is the like I times D part. Okay, so if we just directly simulate this, this would get X, this would get X plus Y, this would get X plus 2Y, this would get X plus 3Y, right? Now let's take an alternative approach of decomposing it into two different arrays, A and B. So now in the A array we need to add X minus Y, and in the B array we need to add Y, right? That's what we discussed. So we add it like partial sums. So we add it, so when we need to add X minus Y to the range 1 to 4, we just add X minus Y to the first cell and subtract that after the range ends. So at R plus 1 we subtract it, right? That's how we do prefix sums. That's how we do partial sums, and finally we would be building prefix sum over that. And similarly for this I times D part, there is this Y, right? So we will add Y in the range 1 to 4, and we would be doing that in a partial sum style again. So we would add Y in the L and subtract Y from R plus 1, and that would actually mean adding Y in this range in the actual array, right? After we build the prefix sum, right? So this is what we are doing in the partial sum. We just add these two values, and then we just take a prefix sum. So suppose we had only this query, so we would have just done this in a separate arrays A and B, and then would have taken a prefix sum. So if you take a prefix sum, we know that this would just contribute in this range 1 to 4, and this would contribute to the range 1 to 4, right? So you would get these two values as prefix sums, like this would be the final arrays. This empty cells would be 0 obviously, and then we combine these two using the combine rule that we talked about, that ARR of I is actually equal to A of I plus B of I times I. So if you see this cell, this is X minus Y plus Y times 1, so that is X minus Y plus Y times 2, that is x plus y, x minus y times y plus y times 3, so that is x plus 2y, x minus y plus y times 4, that is x plus 3y. So we get this array, right? And if you see, these and this is actually exactly same, like all these values and all these values will match correspondingly. So we are actually getting the correct value, and in fact that should be the case, right? Because whenever we are adding it in the range over here in the B, in the actual array after the prefix sum, it would be these contribution over here, and when we combine it using this rule, we are actually doing this itself. So y is getting added to correspondingly as b of I times I in this expression. So we are doing this expression only. Okay, so the final idea is, so we don't do the brute force way, that's obviously there. What we do is that we process all queries first. So given this array, we have a lot of queries, q number of queries. What we do is that for each of the query, what we discussed over here, we add it in a partial sum way. So for each of the query, you add 4 values, right, over here. So for each of the query, you find out corresponding this and this values and add it correspondingly in the A and B arrays. That is like processing all queries first and building this A and B arrays separately. And then once all the queries are done, we build the prefix sum of A and B array and combine it using this rule, okay? And by that we should get the correct answer, because this is like now like a self partial sum problem, and both of them we know that the prefix sum would give us the correct answer across all the queries, and we know that across all the queries this holds true because the queries are addition, and at the cell level we are also doing an addition, so all of the queries are getting multiplied with I itself. So this would work across all the queries. So if you combine them, you will get this corresponding values that were actually equal to the brute force, right? So this is a lot to digest. So first we have the array, we in a hypothetical sense divide it into 2 different arrays, that is A and B, and we know that the actual array that we will get will be of the form A of I times B, A of I plus B of I times I. And now we build these 2 separate arrays. Now each of the queries we decompose it into 2 parts, like one dependent and independent part. So for this dependent part we use the B array, for this constant part we use the A array, right? That's the whole idea. And once we have the A and B arrays for all the queries, we just quickly build the prefix sum and build the answer by combining the A and B arrays, that using the rule that we defined. So like, why do all these complex process? So if you talk about brute force, you can go ahead and like loop over the range and keep on adding things. So that would be order q times n, right? For every query you would need order n time, you need to loop over that. But let's say we are doing it using the partial sum technique that we talked about by decomposing it into 2 arrays and then using partial sum. So for each query you can in order 1 find out the values that are going to be added, okay? That is that dependent and independent part that we discussed about. So dependent parts get added in the range L to R in the A array, and dependent part is in the B array, right? So this is the independent, this is the dependent. So you just get these values added to this range using a partial sum. So we are doing all of this for all the queries, right? So for each of the query you need to add 4 values. So for all the queries you will need just an order q, because for each of the query you need only 4 cells to be updated, so you just do it in order 1. So for all the queries you need order q, right? Now once all the queries are done, you just build a prefix sum for both the arrays. So for both of them you will need order n, so it will be this step over here will need you an order n, right? And after you have built this array, you just combine them using this rule that we defined, and that also takes a linear loop over this, right? Once you have this array, you just multiply like A of I plus B of I times I and put it into the ARR array, that's it, right? So this also takes an order n. So if we go this route for all the queries, we need just order q plus order n plus order n, and that would be order q plus n, right? So you can now process all the queries in order q plus n and get the final array, right? So this is all the technique for this problem. So that's all. See you in the next video.